this module, we are going to talk about HMO approximation, Huckel molecular orbital approximations. And since in the earlier module, we have talked about the approximation methods. So, this approximation is a very drastic approximation which uses linear variation treatment. We are aware of linear variation treatment, and I have talked in details about that. The trial function, and then finding out the eigenfunctions and eigenvalue for small systems like H2 plus molecule ions. All this we talked about in the earlier modules. Okay. Here also we will try to we will be using linear variation treatment, but now the system here is a bit larger system, and we deal with conjugated organic molecules in this approximation, HMA approximation. So HMA approximation is applied to aliphatic and aromatic conjugated systems. Okay, where the basic premise of this is sigma and pi separability. We say that there is no interaction between sigma and pi electrons, and in HMO pi electrons are treated ignoring the sigma electrons. So you see, this is a very huge approximation, because all sigma electrons we neglect, and we suppose that the nucleus of the atoms with which the molecules are formed is frozen, and the only mobile part is the pi electron. So it's a huge approximation. Even then, surprisingly, it gives very good results that we will see. Okay. So pi electron is moving in a potential field created by a frozen sigma electrons and nuclei. So this approximation, I said you, it's a very big approximation. Even then, it gives very good results which matches with the experimental results also. Okay. So this molecular wave functions are obtained by using the same LCAO, linear combination of atomic orbital treatment, and that we have done in details. So any molecular orbital here will be again given as summation of Ci phi I, where phi I are individual wave functions. Now this wave functions will be of what? So suppose if you have a conjugated system like C double bond C, and here you have I will omit one of the bond. Okay. So now is in this single bond C, all this is pi sigma electron. So this, since this is not moving, this is frozen. So what we suppose it that these two orbitals which is present on the two carbon atoms and which overlap to give you pi bonds, this will be only treated. So you have electron 1, you have electron 2 present in the pz orbital, which we will treat in the HMO approximation. So any carbon which is sp2 hybridized will have one pz orbital perpendicular to the plane of the molecule, and this pz orbital's wave function will be used in the LCAO method. Okay. So this phi I represents actually psi p z orbital. Okay. So in HMO this will be psi p z orbitals. So the first approximation, which is very huge approximation, is that we neglect all the sigma electron. We treat only pi electron in HMO approximation. Okay. And these pi electrons, if you have two bonds, one pi bond, then you have two pz orbitals. So it will be a C1 psi pz, C2 psi pz, like a sort of thing. Okay. Now if we go for what we do variation treatment. So a quick recap of what we have already done. In variation treatment of psi MO will give you n into n secular determinant. So if your psi MO is C1 psi 1 plus C2 psi 2, then it will give you 2 by 2 determinant. If your psi MO is C1 psi 1 plus C2 psi 2 plus C3 psi 3, then it will give you 3 by 3 determinant. If your psi MO is C1 psi 1 plus C2 psi 2 plus C3 psi 3 plus C4 psi 4, then it will give you 4 by 4 determinant, and so on. This we have seen earlier. So the 2 by 2 determinant will be H11 minus ES11. You should remember, you should recap, because we did it earlier, and H12 minus ES12, H21 minus ES21, H22 minus ES22. Okay. Then H 3 by 3 determinant you will get from this MO, and it will be H11 minus ES11, H12 minus ES11. So 3 by 3 determinant, 3 terms, 3 rows and 3 columns you will get. And when you are writing 4 by 4 determinants, you can write it like this. See, the one thing which you should remember, that whatever the determinant in determinant 2 by 2, 3 by 2, 4 by 4, 5 by 5, 6 by 6, whatever it is, all the diagonal terms you will see will have similar coefficients H11, H22, H33, H44 and so on. So if you are writing a circular determinant, so then you must see the diagonal terms. If you are written the diagonal terms right, then it means you have written the right kind of circular determinant. Okay, this we already did. It's just recap of the things which you have done. Okay, now what are these? If you remember, these H11, H12 are the different integrals, and HII or Hij is Coulomb integral or exchange or resonance integral. What does it mean? It means all H11, H22, H33, H44 means all these terms are present in diagonal terms. All these are diagonal terms. All these are present in the diagonal terms. So all these are called Coulomb integral. Then Hij means H12, H21, H31 and so on. All are called resonance integral. And then as you know, Sij is called overlap integral. Okay, S12, S13, S14, all is there. Okay, so these are called overlap integral, and they are often represented as S only. Okay, so when you do this variation treatment of these trial functions, then you get n by n circular determinant. So in this HMO approximation, we will not do the actual variation treatment. We will start by writing the circular determinant of a particular system. Okay, so how will you write this? The easiest way to write this is that you have to count the number of pi electron present in the system, or number of electrons which you have to treat. Okay, so if you have a cyclopropene, then you have cyclopropene system, you have only 2 pi bonds, but you have 3 carbon atoms. So each carbon atom will contribute 1 pz orbital, and for that system you will have 3 by 3 determinant. We will see later on. Okay, so now when you write this one, then further drastic approximations are some of the drastic. One was that all sigma bonds are neglected. We are counting only pi bond, the first approximation. Then the second approximation is that all HII and HJJ means H11, H22, H33, H44, which is called Coulomb integral, representing pz orbital present on each sp2 hybridized carbon atom in conjugated molecule, and they are given in an alpha symbol. So alpha is a negative quantity. This you must remember. Alpha is a negative quantity. Okay. So when you have the similar digits in the subscript H11, H22, H33, you will write alpha in place of that. Okay. Then Hij means H12, H3 subscripts a different number, then you write it beta. And when you write it, when I is not equal to G and I and G are the nearest neighbor. This is very important, nearest neighboring atoms. Because if you have a molecule like, say, suppose CH2 double bond CH, single bond CH, double bond CH2. Now you number it C1, C2, C3 and C4. 4 carbon atoms are there. C1 and C2 is directly bonded. It means H12 will be beta, but C1 and C3 are not bonded by sigma bond. So H13 will not be beta. H13 will be equal to 0. That is the second term. Okay, and this beta, this beta is also a negative quantity. Okay, when Hij is equal to 0, when I is not equal to J and I and J are not nearest neighboring atoms and are not directly bonded by sigma bond. So the approximation is that all HII, HJJ will be written as alpha, all Hij will be beta provided I and j are the nearest neighbor. Okay, all Hij will be equal to 0 if I and j are not nearest neighbor. Okay, so these 3 points you will have to remember. And overlap integral Sij is 0, that you know. Overlap integral is what? Sij, if I am writing, then I can write psi I, psi j d tau. Okay, this will be Sij. And what you are using, this psi I and psi j are actually psi pz and psi pz. And what kind of psi pz you are using? What you are using is an orthonormal set of wave functions. Orthonormal wave functions. So the moment you say it's an orthonormal function, then psi pz 1 and psi pz 3 or psi pz 2 or psi pz 3 will be equal to 0. So it's Sij, psi pz I, psi pz j will be equal to 0. Okay. So this obviously becomes equal to 0. No need to write it because it's very simple concept that you already know. Okay. So Sij is equal to 0. Okay. Once we have this, then we can start talking. This is what is the HMO. The concept is this only, that you treat only pi bonds. So when you look at the organic molecules having carbon atoms only, carbon skeleton, for each carbon you treat one psi pz to be free and present on the carbon atom. Okay. So for each carbon atom, for each pz orbital, you will write one wave function in the LCAO. Okay. If it is 4, you will get a 4/4 determinant. If it is 6, you will get a 6/6 determinant. If you have 3 pz orbital, you will get 3/3 determinant. Okay. Once you have written the secular determinant, then the terms present in the secular determinants are again approximated and given a different symbol. So all HII and HJJ, if you have similar number present in the subscript of the Coulomb integral or exchange Coulomb integral, okay, then what you write? HII, HJJ is equal to alpha, given a new symbol. This alpha is a negative quantity. Hij, when you have different subscript, different number in the subscript of Coulomb integral or exchange integral, it will be exchange integral or resonance integral. So all resonance integral which is represented as Hij will given a beta symbol, and this will be beta symbol only when I and j are the nearest neighbor. If they are not the nearest neighbor, then Hij is given a value of 0. Okay. So only these 4 points, if you remember, you can do the calculations of HMO approximation. Okay. So what we are dealing with? We are not dealing with a diatomic molecule here. We are dealing with a larger molecule. We have started talking about quantum mechanics with very simple system, a free particle, a particle in a one-dimensional box. Then we talked about simple harmonic oscillator, 3-dimensional box, rigid rotor, hydrogen atom. Then we went for the molecules, H2 plus molecules, then certain bigger molecules in the VBT, and now we have larger molecules. Okay. So large organic molecules, conjugated dienes. Okay. You can talk about benzene also, a big molecule with 3 pi bonds and 6 pz orbitals. So all those molecules which has a free pz orbital present on the carbon atom which overlap to give you pi bond can be treated by HMO approximation. That's the thing. Okay. So now let us start with a very small molecule, very simple molecule where you have only 2 pz orbitals, and this is a ethylene molecule. So in ethylene molecules, what do you have? You have 2 carbon and 4 hydrogens, and the 2 carbons are bounded by a double bond. So you have 1 sigma bond and 1 pi bond. You have 1 sigma and 1 pi bond, and all carbons, both the carbons are sp2 hybridized. If they are sp2 hybridized, then each of the carbon will have a pz orbital, and it will be a 2 pi electron system, we will say, because you have on the 2 carbon you have 2 pz orbitals. So the system we will call it a 2 pi electron system. Okay. Now in this 2 pi electron system you have, so your psi MO will be C1 psi 1 plus C2 psi 2, and if you write C1 means two wave functions we are using in LCO. So what you will get? You will get a 2 by 2 determinant. So the 2 by 2 determinant will be like this one. We have written earlier also. H11 minus ES11, H12 minus ES12, H21 minus ES21, and S22 minus ES22. Okay, these are the 4 terms. And this, you remember this we get from the linear variation treatment when you have an equation, 2 equations, H11 minus ES11. Just to recap, H12 minus ES12 is equal to 0, and then C1 H21 minus ES21 plus C2 H22 minus ES22 is equal to 0. So you get 2 linear equations with 2 unknowns, then you can write the coefficients as the determinant. Okay, and this you get when you differentiate energy with respect to C1 and equate it to 0, and this equation you get when you differentiate energy with respect to C2 and equate it to 0 for the linear variation treatment. Okay, now I hope you are able to recall. Okay, so this is the secular determinant which you can write. Now I said you that in HMO approximation we change the representation. So H11 and H22 will become what? Will become alpha. Okay, so after changing the representation, you see all overlap integral Sij is equal to 0 and Sii Sjj is equal to 0. Once again it is written, approximations are written, all overlap integrals. Then all diagonal terms will be alpha minus E, because S11 will be equal to, in all diagonal terms you have similar number in the subscript of H and S, H11 ES11, H22 ES22. So I said you S11 and S22 will be equal to 1 and H11 will be given an alpha symbol. So it will be alpha minus E, it will be alpha minus E. Okay. So since both the carbon atoms are nearest neighbor, and now here we said that all those carbon atoms which are nearest neighbor, now here you have only 2 carbon atoms, they are bonded by a sigma bond. So both are neighbor of each other. So what we say, this any resonance integral H12 or H21 will be equal to beta. So what you write is, now S21 or S2, what will happen to S21 and S22? It will be 0 because of the orthogonality, because the wave functions are orthogonal. So because of the orthogonality it will be 0. So sorry, but here you don't have here you have S21. So S21 will become equal to 0, Sij is 0. So this will become 0, this will become 0, this will become alpha, this will be equal to 1, this will be equal to beta, this again will be equal to beta, this again will be equal to alpha, H22 alpha, then S22 again equal to, S22 will be equal to 1 and this will be E. So what do you have? You have alpha minus E, then the second term is beta in the first row, in the second row beta minus 0, so beta, and now alpha minus E. Okay. So the determinant changes to alpha minus E, beta into alpha minus E. Now we have to solve this determinant, and for the solution of this determinant, what you do, you suppose the alpha minus E divided by beta is equal to x. Okay. So that energy becomes equal to alpha minus beta x. Rearrangement will give you energy is equal to alpha minus beta x. Okay. So what you can write this, when you suppose this alpha minus E divided by beta is equal to x, so you divide this all the terms in the determinant by beta. So the first term will be alpha minus E divided by beta, so first term will become x. Second term will be beta divided by beta will give you 1. Then in the next line beta divided by beta will be 1 and alpha minus E divided by beta will give you x. So one simple determinant you have 2 by 2 determinant, and you know this value you can find out. So this, the value is x square minus 1 is equal to 0 and x is equal to plus minus 1. Okay. So x has 2 values, one is plus 1, another is minus 1. Okay. If you put x is equal to plus 1, then what will be the energy? Energy will be alpha minus beta. And if you put alpha is equal to minus 1, then the energy will be alpha plus beta. Okay. So, the two energy values are alpha minus beta and alpha plus beta. Now, if you have to decide that which of these will be bonding molecular orbital and which will be the anti-bonding molecular orbital, then I said you in the earlier approximation that both alpha and beta are negative terms. Okay. So, this alpha plus beta will have a higher negative value as compared to alpha minus beta. So, the lower energy will be bonding molecular orbital, and we say alpha plus beta is bonding molecular orbital, lower energy level, and alpha minus beta will be high energy level and will be anti-bonding molecular orbital. Okay. And I have written, remember both alpha and beta are negative quantities. Okay. So, what we did? We started with a system, ethylene molecule, we applied HMO approximation, we found the value of x, we found the value of energy, and now we have two different energy values because x has two different values, plus 1 and minus 1. Okay. So, it means two quantum state we have defined, and now if you have defined two quantum state, then the next target is finding out the wave function for these quantum states. Energy is fine, but finding out the wave function for the energy state. So, how to find out the wave function? And what we did? We did here in this case, I said you, we assume the wave function psi mo to be equal to C1 psi 1 plus C2 psi 2. Okay. Or we can write psi mo is equal to A1 psi 1 plus A2 psi 2. Both could be the same thing, where A1 and A2 are the coefficients. So, since I have used the A1 and A2 later on, so what you can write? What you can write is psi mo, if you write A1 phi 1 plus A2 phi 2, then we can write two simultaneous equations. Now, remember this one, your determinant was this is equal to 0. Okay. So, if this is equal to 0, then you can write the first row and second row as two different equations with the same coefficients A1 and A2. So, the first row you have A1 alpha minus E plus A2 beta, and the second row is A1, and which you can write as A1x plus A2x, because this determinant was also x1 and 1x. So, if you use this determinant, you write this one. If you use this determinant, you write this one. Both equations you can write. Okay. In terms of x also, in terms of alpha minus E also. Same way, you can write for the second row A1 beta, A2 alpha minus E. So, this you get from this equation, second row, and from the second row of x determinant, this determinant, you get A1 plus A2x. Okay. So, both these are writing the determinant from the simultaneous equation and writing the simultaneous equation from the determinant, vice versa, that you should know. Okay. Now, if you have this one, then what you can do is A1 x is equal to A2. Okay. So, A1 x is equal to A2 is equal to 0. Okay. What you can write? Then A1 is equal to minus A2. If the x is plus 1, for x, because x we have determined as plus minus 1, remember. So, x is plus minus 1 means for x is equal to plus 1, what you can write? A1 is plus A2 is equal to 0. So, A1 is equal to minus A2, and for x is equal to minus 1, you can write A1 plus A2x. So, it will be A1 is equal to A2. What does it mean? A1 is equal to plus minus A2. Okay. A1 is equal to plus minus A2. Now, from normalization condition, A1 square plus A2 square is equal to 1. Look at the normalization condition. For the wave function, this one, psi mo, A1 phi 1 plus A2 phi 2, you have And if you write the normalization condition, what do you write? You write psi MO multiplied by psi MO d tau is equal to 1. So, what you write? Integral of A1 phi 1 plus A2 phi 2 and A1 phi 1 plus A2 phi 2 d tau is equal to 1. Now, multiply this one and write the separate integral. A1 and A1 will become A1 square, and what will be the integral? Integral will be phi 1 and phi 1 d tau. Then A2 multiplied with A2 square, and what will be the integral? Integral will be phi 2 and phi 2. So, phi 2 is phi 2 d tau. Then multiply A1 with A2, and what you get? A1 A2 phi 1 phi 2 d tau. Then multiply A2 with A1, it will be A2 A1 phi 2 phi 1 d tau, and this is equal to 1. So, you have 4 different integral: phi 1 d tau, phi 2 d tau, phi 1 d tau, and phi 2 d tau. In this all 4 integrals, the wave functions which you are using is phi 1 and phi 2, and I said you this is for the pz orbital, okay, and this pz orbital wave function is orthonormal wave function. So, what does it mean? Any phi 1 phi 2 d tau and any phi 2 phi 1 d tau will be equal to 0. So, this will go, and if it is orthonormal set, then if you have phi 1 d tau, it will be equal to 1. If it is phi 2 d tau, it will be equal to 1. So, what do you get? You get A1 square plus A2 square is equal to 1. So, that is what is the condition. Okay, I have written here directly and I solved it. Okay. So, from the normalization condition, what you get is A1 square plus A2 square is equal to 1. And remember this gives you A1 is equal to plus minus A2. What does it mean? A1 and A2 are similar terms. So, you can write 2A1 square is equal to A1 is equal to 1, and A1 square is equal to 1 by 2. So, A1 is equal to 1 by root 2, and if A1 is equal to 1 by root 2, A2 you can write as 1 by root 2 also and minus 1 by root 2 also, because A1 is equal to plus minus A2. So, both coefficients will not be same, otherwise the function will be same. Okay. So, A1 phi 1, A2 phi 2, you have 2 different quantum states. So, you need 2 eigenfunctions, and if you put A1 since A1 is equal to A2, so A1 is 1 by root 2 and A2 is 1 by root 2. So, you can write only one eigenfunctions. You cannot write 2 eigenfunctions. So, in order to make it so, you write A2 is equal to minus 1 by root 2. Now, now what we can write is, so thus the one of the wave functions will be psi 1 will be 1 by root 2 psi pz plus psi pz for bonding molecular orbital. Okay. Another wave functions which you can write as 1 by root 2 psi pz minus psi pz, because A2 is equal to both plus minus root 2, so anti-bonding molecular orbital. And corresponding to this, if you look at the pi bond energy, okay, so what does it mean? It means you have 2 different states. One is bonding molecular orbital, another is anti-bonding molecular orbital. One is given 1 by root 2 psi pz plus psi pz plus. Another is given 1 by root 2 psi pz minus psi pz. And how many electrons you have in the ethylene molecule? Pi electrons, you have 2 pi electrons. So, both these pi electrons are here. And what is the energy? Energy is alpha plus beta for this one, alpha minus beta for this one, for anti-bonding. Since both the 2 electrons are present in bonding molecular orbital, so the pi bond energy, if you calculate for 2 electrons, this is number of electron, and alpha minus beta is the energy of bonding molecular orbital. Now, what I have given you? Minus 2 alpha. Minus 2 alpha is the energy of electron when it is free, when it is not bonded. Okay. So, if you deduct this minus 2 alpha, then the total energy which you get is 2 beta. Okay. It means as compared to, sorry, it is already there. Okay. So, as compared to the free electrons, the electrons are more stable when they are bonded, and the stability is equal to the energy of 2 beta. Okay. So, this you get, and if you draw the molecular orbitals and the binding, then this is a positive combination of linear orbital, and this is a negative combination of linear orbital. Okay. So, when you write positively, then both the symbols, both the lobes are positive, and one lobe will become negative if we do the combination in the anti-bonding mode. Okay. So, you have two different molecular orbitals and two different molecular orbitals for ethylene molecule, and the lower energy orbitals is occupied by the 2 electrons of the 2 pi electrons. Okay. So, and the stabilization energy which you get is equal to 2 beta. Stabilization energy which you get is equal to pi bond energy which you get is equal to 2 beta. Okay. Having done this, what you can do is we can find out electron density, charge density, and bond order also. It is the same thing which I did earlier. You see, there I have written A1 and A2, and here it is AI. So, if you have the normalization condition, what do you write? AI square, Pi square, and this will be AI, Aj, Pi, Pj, d2 is equal to 0 and I is equal to j. So, it will be this one, and from the normalization condition, what you have is A1 square plus A2 square I have written. Okay. So, it is the same thing which we did earlier in terms of A1, A2, and more easier to understand. Okay. So, where this A refers to coefficients A1 and A2, and P refers to phi 1 and phi 2, which is a function. So, this function Pi, Pj, d2 is equal to 0 for I not equal to j. Okay. And if equal to 0 for, and if they are equal, then it is equal to 1. Okay. So, Pi square will be equal to 1, and it will give you this one. Okay. This we already did it in the previous slides. Okay. Now, having done this, if you have the coefficients, then psi a square represents the electron density at atom 1 due to 1 electron. Depending on the number of electrons in the HMO, the electron density can be calculated. So, if you have to calculate the electron density, then the number of electron you have to see, and the coefficients you have to square of the coefficients, where Aij is the coefficients of atom I in jth HMO, and Nj is the number of electron in the jth HMO. Okay. So, whatever you have the electron present in the bonding molecular orbital. So, electron density at carbon number 1 due to pi electron will be A1 square, and what is the coefficients? 1 by root 2. So, a square of 1 by root 2, it will be 1 by 2, and at carbon number 2 again the coefficients is A2 square. So, it is 1 by root 2 square, at both the places it is the same coefficient. So, 1 by root 2, and the total in ethylene 2 pi electrons are in psi 1. Okay. Both the electrons are in first wave functions. So, on each carbon atom the electron density is equal to 1. So, electron density we have calculated. Now, if you have to calculate charge density, then charge as a neutral carbon atom is assigned an electron density equal to 1. So, if its electron density is equal to 1, the charge present is 0. So, the net charge density is 1 minus Qi, where this is Xi I represents the charge density and Qi represents the electron density. So, electron density we have found equal to 1. So, at both carbon atoms the charge will be 0. At both carbon atoms the charge will be 0. Okay. Now, bond order if you have to calculate, then you have to look at the number of electrons which is present in the orbitals, in the molecular orbitals. Okay. And then what you do, you look at the number of electron which is present, and then the coefficients of the 2 carbon between which you are calculating the bond orders. Okay. So, if you have the this is what is the coefficient. So, the electron is present only in psi 1, only in psi 1 you have the electron, and the coefficients is 1 by root 2 for both. So, in between C1 and C2, the C1 coefficient is 1 by root 2, C2 coefficient is also 1 by root 2. Okay. So, this represents at C1, this represents at C2. Okay. So, it will be bond order between carbon number atom 1 and 2 will be 2 multiplied by 1 by root 2 multiplied by 1 by root 2 will be equal to 1. So, everything which you get is ethylene molecule is neutral, that we proved. Ethylene molecule has only one pi bond, that we proved, that bond order is 1. Okay. Ethylene molecule has, if it's forming a pi bond, it will have two molecular orbitals, pi bonding and pi anti-bonding, and both will have the wave functions that we determine. Okay. So, we calculated the eigenvalue, we calculated the eigenfunction, we calculated the electron density, we calculated the charge density, and we calculated the bond order for one of the simple molecule, ethylene molecule, from scratch by assuming HMO approximations. And all the results which we have obtained is what we already know about the ethylene molecule. Okay. So, even after this drastic approximation, we get the results which we already know and which is a fact. Okay. So, this HMO approximation is widely applied for organic conjugated molecules. We will see some other examples of HMO approximation in the next module. Thank you.